Hey everybody, welcome to lesson 5 of unit 2, complex zeros. Let's go ahead and get started. So the fundamental theorem of algebra states that a polynomial function of x with a degree n has n number of complex zeros. So we've been using this as we've been studying that if it has a degree, that's the maximum number of zeros that it can have. That can be real and non-real. And that's what a complex number is. It can have real components and non-real components. Some of these zeros may be repeated. So last lesson, when we were talking about Descartes' rule, that we figured out that some zeros could be positive, some could be negative, some could be imaginary, meaning non-real. The linear factorization theorem says that if some function f of x is a polynomial function where n, the degree, is greater than 0, then f of x has precisely the number of n linear factors. Remember that a linear factor usually looks like x minus some number c, which is a constant. So the fundamental polynomial connections in the complex case mean this. The following statements about a polynomial function of f are equivalent if k is the complex number. So we say x equals some number k is a solution, or aka root or 0 of f of x. If we set it equal to 0, we talked about this before, we say that k is a 0, aka solution, aka root, of the function f. And then we say x minus k is a factor of f of x. This is all a review, things that we've learned before. The conjugate root theorem, so this should sound familiar to you. We talked about complex conjugates back in our prerequisite season before we started Unit 1, that if p of x is a polynomial with rational coefficients, then the irrational roots of p of x, where p of x equals 0, occur in conjugate pairs. Remember, that means any complex number happens with its conjugate pair. So that is when a plus root b is a root, then so is a minus root b. Keep in mind that a and a are both the real components. They're the same. The root of b will be the non-real component. And then the sign in between them, one is positive, one is negative. They're opposites. That's why we call them conjugates. But it's also a root. Also, if a plus bi is a 0 of the function, then a minus bi is a 0 as well. We call that also the complex conjugate. Okay, keep in mind that a complex number, remember that a complex number always has two parts, where a is the real part and the imaginary part always has usually has a coefficient in front as well. All right, let's do some examples. So this first example, number 1, it says find a cubic polynomial equation with the roots at root 2 and 5. Leave it in factored form. Well, here's what we know about the root of 2. Because we know that this is an irrational number, it also will have a root of x equals negative root of 2. They go in conjugates. So we say the factored form will be that f of x could equal x minus root 2, but also x minus negative root 2 and x minus 5. Okay, if I want to simplify that, I put x minus root 2 minus a negative, it would be a positive, and x minus 5. And then you could expand that to find your function. But this is written in factored form. Example 2, it says write the polynomial function in standard form and identify the zeros of the function and the x-intercepts of the graph. If f of x equals x plus 2, x minus I root 3, and x plus I root 3. So here's what this means. It says write the polynomial function in standard form. Remember, standard form is an expanded form. So we're going to multiply this out. Anytime that I see two conjugates, we're always going to focus on those two things first. Remember, when we're multiplying factors, we can only multiply two at a time. We're going to use FOIL to multiply this one. So we're going to go first, x times x is x squared. Outer, x times I root 3 is a positive. Basically, I root 3 times x. Inner, negative I root 3x. And last, we'll get a negative I squared and a root 3 squared as well. Let's simplify this. Well, I know I root 3x minus I root 3x will cancel. Root 3 squared, those cancel. This just becomes a 3. I squared is really a negative 1. So what we're really dealing with here is a minus times negative 1 times 3. And then we have our x squared here. So we know negative times a negative is a positive. 1 times 3 is 3. So this becomes x squared plus 3. So this essentially is all of this. Don't forget that we still, once we have all this broken down, we still need to multiply this one down. So we've got x plus 2 now. And now we're going to FOIL these two together. So we can multiply x times x is x to the third, or x squared times x is x to the third. Outer is 3 times x. Inner is 2x squared. And last, we've got plus 6. Put this in standard form. We want it to be descending order. So we'll put the highest degree and then down from there to our constant. So this is our function f of x, written in standard form. And then when it says to also find the zeros, the way that we're going to do that is we're going to take those factors that we had here to find the zeros and set them equal to 0. So we know x plus 2 times x minus I root 3 times x plus I root 3 all equal to 0. Therefore, I can set each of these equal to 0. So we get x equals negative 2, x equals positive I root 3, and x equals negative I root 3. We also know, because this is in, this is in our standard form here, that our c value, or that last constant value, is 6. So therefore the y-intercept is 0, 6. All right, let's go ahead and talk about finding a polynomial given complex zeros. So here we've got an example where we're going to write a polynomial function with a minimum degree in standard form that's expanded. Remember, when we say standard form, we have to think expanded form with real coefficients whose zeros include the following. So we see a 0 of negative 3, negative 4, and 2 minus I. Remember, this is a complex number. And when we see a complex number, we know complex roots always come in pairs of complex conjugates. So because there's only one here, I know there must be another. We're going to write its complex number. So we know the first term is 2, the last term is I, but the middle is going to be the opposite of the minus, which is a plus. So actually there are 1, 2, 3, 4 at a minimum roots here. So what we're going to do now is we're going to set this up. And we're going to say that f of x equals, and now we're going to set all these zeros up into factored form. So we're going to say 1, 2, 3, 4 roots. And we start with x minus at all of them. So we've got minus 3, minus 4. We're going to put it in its own parentheses, 2 minus I, and in parentheses 2 plus I. Okay, because we want to keep that minus separate for now. Keep in mind when I'm foiling all these together, again, you're going to multiply the conjugates first. So let's multiply these first. I'm going to rewrite this so we can distribute those negatives. So we've got x minus 2 plus I and x minus 2 minus I. So now when I go to FOIL this, you could either FOIL or you can use box method. I'm going to use FOIL here, so we get x squared minus 2x minus ix minus 2x positive 4 and positive 2I. And then last, we've got positive ix minus 2I and minus I squared. If I look through this, I'm going to look for like terms. I know negative ix and positive ix cancel. Positive 2I and negative 2I will also cancel. And then this I squared, we remember, is just really a negative 1. So a minus a negative 1 is really plus a positive. So we've got x squared minus 2x, and minus 2x is minus 4x. Positive 4 and plus 1 is plus 5. So that's our complex conjugate roots multiplied. Now let's go ahead and multiply these two. Remember, minus and negative becomes positives, so we end up with foiling x squared plus 4x plus 3x plus 12. Simplify that, we get x squared plus 7x plus 12. Now we need to multiply one more time all of this together. So we're going to multiply these three terms times these three terms. All right, let's do it in different colors. So first, x to the fourth, negative 4x to the third, positive 5x squared. Let's do 7x times x squared is 7x to the third. 7x times negative 4x is negative 28x. 7x times positive 5 is positive 35x. And we'll use purple. 12 times x squared is positive 12x squared. 12 times negative 4x is negative 48x. And 12 times positive 5 is positive 60. Now we're just going to clean this up, combine like terms where we can. I see that we've got negative 4x cubed and 7x cubed. I see 5x squared and 12x squared. And I see negative 28x, positive 35x, and negative 48x. So if I combine all these like terms, we get x to the fourth plus 3x to the third minus 11x squared minus 13x plus 60. And there's our simplest polynomial with those four roots. So let's set up the next one. F of x has 0 at x equals 1 with the multiplicity of 2. Remember that it happens twice, so that means x minus 1, and it happens again, another x minus 1. We also have a root at 1 minus I. That's a complex number, which means I know that it also occurs as a conjugate, so that x also will have to equal 1 plus I. So when I set up those two roots, we're going to go x minus, and in the conjugates there, we're going to use them in their own parentheses, 1 minus I and 1 plus I. You're going to do the same thing that we did before. We're going to FOIL. Let's do our complex first. So this is going to become x minus 1 plus I, distributing that negative. And this becomes x minus 1 minus I, distributing that negative as well. And now we're going to FOIL. So x squared minus x minus ix, negative x, positive 1, positive I, and lastly, positive ix minus I squared. Let's clean this up. Look for some i's that will cancel. That's the thing about those conjugates, that they're always going to cancel out those weird i's. And then we see that I and negative I will also cancel. And then, of course, I squared really is a negative 1. When I subtract a negative 1, I get a positive. So I'm really dealing with here x squared with these two negative x's. So there's two of them. Then I've got positive 1 plus another one that's positive 2. So that's what all of that multiplied down to as far as the last two complex roots. Let's go ahead and multiply these two here. I know we're going to have x squared minus x, and positive 1. If we simplify that, we get x squared minus 2x plus 1. And lastly, we're going to distribute these two again. So we're going to go first, middle, last. And do it again here. We go middle to the first, middle to the middle, middle to the last. And the last number 1 to each of those three. Combine your like terms. And we get a total of g of x can equal x to the 4th minus 4x cubed plus 7x squared minus 6x plus 2. Okay. Now let's go ahead. Once we've got a huge polynomial, we're going to factor it having a complex 0. So what do we know? Okay, so first we're going to find all the zeros and factor f of x over the set of complex numbers. Okay, so remember we're going to use our rational roots theorem. We're finding all of our factors of p over factors of q. Remember that our constant term is p, our leading coefficient term is q. This is helpful to us because all of our factors are just of 1 are 1. So all of the factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. What we're going to start to do is we're going to be looking for all of these numbers, which of them are going to have a remainder of 0, which will give me the zeros, get that down to a quadratic term, and then solve for the irrationals. So here's what we're going to do. Let's pick, for funsies, let's pick -1. Let's try it. So we're going to set this up using our coefficients. So 1x to the 5th minus 3x to the 4th minus 5x cubed plus 5x squared minus 6x plus 8. That was in descending order, no missing terms. We bring down our first term, and now we multiply box times the bottom. That gives me my next number is -1. Add down, we get -4. Box times the bottom, we get +4. Add down. Multiply again, we get +1. 6, multiply again, -6. Ooh, I don't know if this is going to work. Okay, this does not work, so we are not going to choose this one. So -1 isn't a thing. Let's try +1. So we're going to use our same numbers that we used here. 1, -3, -5, 5, -6, 8. And we're going to do the same process. Bring it down, multiply, add down. Multiply, add down. Multiply, add down. Multiply, add down, multiply, add down. Okay, so we've got a remainder of 0, meaning this right here, 1 is a 0. This tells me that we have all of this is equal, but now instead of starting back over, these remaining terms as my remaining leftover polynomial, I'm going to look for another 0. Let's try, for funsies, let's try +4. So now we're going to use these numbers that were left over that represent our remaining polynomial and see if it works. If it's a remainder of 0, then we know it's a solution. Bring down the 1, let's multiply, add down, multiply, add down, multiply, add down, multiply, add down, and this is a solution, which means I'm not quite down to a quadratic yet, because remember this would be 2x to the zeros, 1x, 2x squared, and 1x cubed. So this tells me I need to find one more 0 until I can get it down to a quadratic. Let's try -2 for fun. So I'm going to put this into those leftover polynomial coefficients. Use synthetic division, bring down the first number, multiply, add down, multiply, add down, multiply, add down, and we do have our last 0. That's a solution. This tells me I have 1 and 1x squared. So what we're going to solve now is we're going to say 1x squared plus 1, set it equal to 0. Because this is a quadratic, I can solve this directly. There's no x term, so I can actually subtract 1 from both sides. And I've got x squared equals -1. When I take the square root of both sides, it's plus or minus. So I get x equals plus or minus the square root of -1 is just I. So what are all of our zeros? So our zeros we just found were here. And they're at, we tried this one, 1, 4, -2, and then we have positive I and negative I. So those are our zeros. If we wanted to put them in factored form, our factored form, remember, is going to look like this, where we put them in x minus 1, x minus 4, x minus -2, which will be a positive 2, x minus I, and x plus I as well. Okay. We're going to skip that next one. We'll come back to that. We're going to factor over some real numbers. So write f of x equals 3x cubed minus 2x squared plus x minus 2 as a product of linear and irreducible quadratic factors, each with real coefficients. That is, factor over real numbers. We're going to think about different forms here. Actually, we're going to skip over to example number 8. This is going back to what we learned in another section. So we're going to sketch the graph of the polynomial function with the given zeros, multiplicities, and sign of the leading coefficient. We know that -3 is a 0 with a multiplicity of 2, 4 is a 0 with a multiplicity of 3, and a is positive. So here's what this means. If it has a multiplicity of 2, it touches or bounces it, right? So this tells me that the root is x minus -3, which will be plus 3, and it's going to have a multiplicity of 2, which means we're going to square it. And then we'll have x minus 4 at that root, but we're going to have a multiplicity of 3, so it's going to get a cube root, okay? Keep in mind, we know that our degree will have to at least be 2 plus 3 is 5, because we're going to add the sum of those exponents. So here's what we know. We also know by the remainder theorem that if I want to find the y-intercept, I need to know, hey, if the y-intercept is 0, comma, whatever the y-intercept is, that when I evaluate f of 0, it's going to be whatever the y-intercept is. So what I can do is I can take this very basic polynomial I've just written, and I'm going to evaluate it. If this is f of x, I'm going to say, what's f when x equals 0? So if I go like this, 0 plus 3 squared times x 0 minus 4 cubed, I get 3 squared is 9, and -4 cubed is -64. If I multiply those two, I get -576. This gives me the y-intercept. So I can say that the y-intercept is 0, -576, which was really low. I also know that if a is positive, that my leading coefficient will also be positive. And this will give me my end behavior. So I know that my limit as x approaches -infinity, because our degree is odd, will be going down to -infinity. And that my limit as x approaches positive infinity will be going upwards to positive infinity. So if I draw this on my graph here, that we have a multiplicity of a 0 at -3 of 2, and we have also a 0 at 4, We know the degree is 5. We know on the right side it's going up to infinity. On the left side it's going down to negative infinity. And we know at -3 it's going to touch or bounce. So we know it's not going to cross through the x-axis. We know it's going to touch the y-axis. We'll call this point here 0, -576. Don't worry, it's not drawn to scale. So we know it's going to cross here somewhere, somehow. And then it's going to come back up and it will go through when x equals 4 because it has a multiplicity of an odd number. All right, we're going to practice the rest together in class. We'll see you then.